Let us relearn those math skills to bridge the gap. For the second session, our topic is derivatives. And if you are here without watching the first part, I highly recommend you to watch that first because this is just a continuation of it. I have the same disclaimer as we talked in the first part. What are we going to learn today? We will try to understand the meaning of slope, the concept of derivative df by dx, the partial derivative dou f by dou x, and the total derivative or the substantial derivative capital df by dt. What is the slope? Yes, you're right, the idea is the same as you're thinking right now. The granny here is enjoying the slope of the slide. In fact, it's more fun here because of the variation in the slope. Now let us consider a linear function. For a linear function like this, it is very easy to calculate the slope. It is the ratio of the change in y to the corresponding change in the x value, or the ratio of rise to that of the run, which is nothing but the ratio of vertical distance and the horizontal distance one needs to travel from, let's say, a point B to reach the point C. The value of the slope can be positive or negative, which indicates whether the function is going to increase or decrease respectively. And more importantly, one must note that the slope of a line is the same at any point on the line. Now, what if the function is not a straight line? Then obviously the slope will change at every point on the curve. The correct way to find the slope at any point on the curve is to find the slope of the tangent line at that particular point. And this slope will give us an idea of how the function is going to vary, whether it's going to increase or decrease with the change in the value of x, or it indicates the rate of change. It is easy to understand looking at it graphically. But how to find the value of slope without actually drawing the tangent line every time? Let us find it out. For that, consider a quadratic function, which is obviously not a straight line, but a parabola. So the slope changes at every point on this curve. Now let's try to find a way to determine the slope at any point on this curve. If we take a point P on it, we know that the slope at P will be the slope of the tangent line passing through P. Now consider a point A which is very near to P on the line. The line passing through the points P and A is called the secant line, as shown in the red color here. Let the horizontal distance between P and A be delta x, and the vertical distance will be nothing but the difference in the value of function, which is f of x plus delta x minus f of x. Now if we try to reduce the value of delta x, the point A will come closer and closer to point P. You can see that the secant line is becoming almost same as the tangent line now. So at a point when delta x equal to 0, that is when the point A coincides exactly with point P, what will be the slope of secant line? It will be the same as that of the tangent line. Now let us try to formulate what we have observed geometrically here in the form of an equation. The slope, that is the ratio of change in the value of function delta f with a small change in delta x, is equal to df by dx, that is nothing but f of x plus delta x minus f of x divided by delta x, when the limit delta x tends to 0. That is very important. That is when delta x is coming closer and closer to 0, but not 0. This is called derivative, written as df by dx or f dash or sometimes even f dot. And all these formulas which we memorized for our exams, like dy dx of x power n, dy dx of sin x, dy dx of cos x, everything can be easily derived based on this expression. Now let's see the derivatives of displacement. If x is the displacement, and if we take the derivative of displacement with respect to time, that is dx by dt, we will get the rate of change of displacement with respect to time. That is nothing but velocity, that is the speed. Now what about the rate of change of velocity? That is how fast or how slow velocity is going to change. That is the second derivative of displacement, d square x by dt square. That is nothing but our acceleration. Now what if we take the third derivative of displacement? That is the rate of change of acceleration. It is known as jerk. And it doesn't stop there. The fourth derivative of displacement is called snap. The fifth derivative of displacement is called crackle. And the sixth derivative is called pop. Now you may be wondering, I have experienced only up to acceleration. What is the physical significance or the physical meaning of all these higher derivatives, right? Well, if you meet with an accident, you are most likely going to experience higher derivatives of displacement. Not only that, if you are new to driving and learning to smoothly accelerate a car, then you are very likely to experience jerk. Fighter jets and fighter jet pilots often experience high g-force and higher derivatives of displacement. Here you can see a person who gets unconscious when he experiences high g-force and jerk in a flight simulator. These higher derivatives of displacement has also some very interesting applications. For example, in amusement parks, the roller coasters are designed based on these higher derivatives of displacement. In manufacturing industries, if we want to avoid wear and tear or to have longer life for the tools, higher order derivatives of displacement of these tools should be avoided at any cost. Other practical applications of derivatives are in the form of ordinary differential equations or ODEs. For example, we can write the equation for the displacement of a falling stone due to gravity in the form of a differential equation using derivatives. Similarly, the velocity of a parachute, the transient water level of a tank with an outflow, the displacement of a spring mass system, the value of current in an RLC circuit. We can also write the differential equation using derivatives to find the value of theta of a simple pendulum, beats of a vibrating system, the deformation of a beam under some load. So there are tremendous practical applications of derivatives. Now let's move on to the next topic, that is the partial derivative or dou f by dou x. To learn partial derivative, first we need to understand the multivariable function. Until now we have seen only a single variable function, which was either a function of x or a function of time and was represented by a single curve. On the other hand, a multivariable function is a function of two or more variables, like say f of x, y, or a function of x, y, z, and t, and so on. Let us see an example. In the 3D coordinate system, a function f of x, y can be plotted as a surface. Like, if f of x, y is equal to x square plus y square, then it will look like a surface made by revolving a parabola about its axis. Let's see one more example. F of x, y is equal to 2 sine square x divided by square root of y square plus 1. So this is a function of two variables. This looks like several parallel mountains that are periodic or repeating, as you can see here. And that periodicity is because of the presence of a sine component in the function. So these are multivariable functions, and now let's try to understand partial derivative. To explore the concept graphically, let us plot a function f of x, y is equal to x square plus y square divided by 2 in the 3D space, which is nothing but a surface here. If we plot y equal to constant in the 3D space, it will be a plane that is normal to the y-axis. And if the value of y is equal to 0, then it will be passing through the origin. You can notice that this plane intersects our function, and the point of intersection or the point of contact between the function and the plane is a curve. In this case, the curve is a parabola. Now, dou f by dou x is nothing but the derivative of the function when the value of y is constant. So that is the slope of our intersection curve, and the value of the slope is going to change at different values of x. Similarly, we can find dou f by dou y by keeping x equal to constant and taking the slope of the intersection curve of the plane x equal to constant and the function, and finding the slope of this intersection curve at different values of y. So if we keep x equal to constant, we get the partial derivative dou f by dou y, and if we keep y as constant and find the derivative or slope of the intersection curve, we get the partial derivative dou f by dou x. So that's all about partial derivative, which is nothing but the slope of our intersection curves. The practical applications of partial derivatives are in the form of PDEs or partial differential equations. Partial differential equation is nothing but the language of God, or you can call it as nature. The governing equations of all natural phenomena are written in the form of partial differential equations. Let's see some of the interesting applications for mechanical engineers. For example, the heat conduction equation. And in fluid dynamics, the conservation of mass, conservation of momentum and energy. Here you can see a set of equations for the conservation of momentum, known as the famous Navier-Stokes equation. There are several other physical phenomena like acoustics, vibration, etc., which are mathematically expressed in the form of partial differential equations. Now, the last topic for this video is the total derivative, or sometimes known as substantial derivative or the material derivative, and is written as capital D by dt. This is one derivative which is very important for mechanical engineers or those who are interested in fluid dynamics or aerodynamics or in any transport phenomena. A total derivative of a multivariable function of several variables, and each of these variables are again a function of another argument. For example, a function f, which is a function of x, y, z and t, and the variables x, y and z are also a function of t, then the total derivative is equal to the sum of partial derivatives with respect to each variable times the derivative of that variable with respect to the independent variable. In fluid dynamics or aerodynamics applications, the total derivative is written as the sum of partial derivative of the function with respect to time, known as the local derivative, and then the convective derivative, which involves the velocity component. To understand the different terms here, let us consider a 3D Cartesian coordinate system and a small fluid element at an initial position at time t1. We know that the velocity v is a vector and can be expressed as the sum of three components u, v and w in the x, y and z directions respectively. If the fluid element moves to another position, and if we try to find the rate of change of any scalar property of the fluid element, let's say like density, then it can be written as capital D rho by dt, where rho is the density, is equal to dou rho by dou t, that is the partial derivative of density with respect to time, and then the convective part, which involves velocity u dou rho by dou x plus v dou rho by dou y plus w dou rho by dou z. The first part represents the time rate of change of density of the fluid element at a fixed point, and the second term represents the time rate of change due to the movement of the fluid element. Now, if you are still not clear about this concept, let us consider a simple example. Imagine that you are on a beach and enjoying the sea. And the scalar property or the function which are interested here is the temperature of your body. If you were in water, obviously your temperature was different. And now if you start walking along the beach, your body temperature starts changing due to the movement or the change in your position. This change in temperature is analogous to the convective derivative. Now imagine that your girlfriend comes there and gets angry at you for some reason and throws an ice cream at you which she was eating. This for sure is going to change your temperature instantly. This momentary change in temperature is analogous to the local derivative. So the net change in temperature is the sum of local and the convective derivative, and this is known as the total derivative or the substantial derivative or material derivative, written as capital D by dt. So that's all for today, and in the next video we will talk about vector and its operations. If you like this video, please hit the like button and subscribe to the channel for more interesting videos. See you in the next video. Bye bye.